Hello, my dear students, my bachas, welcome back. I'm so happy to see you. Your exams are just around the corner, and I know you're working so hard, so let's get you fully prepared. Today, we are going to master a really important chapter, current electricity. Now don't you worry, it's not some big scary monster. It's actually a very simple story. A story about getting tiny little charges to move.
So, here is our game plan for getting full marks. First, we're going to think of electricity as a river. Then, we will learn its most important rule, its golden rule, Ohm's law. After that, we'll take a microscope and peek inside the wire to see what the electrons are really doing. We'll discover how cells give them power, and finally, we'll unlock two super tools, Kirchhoff's rules, to solve any circuit. And yes, we'll finish with a real exam question. Ready to do this? Cholo, let's go!
Okay, so first things first, let's get to the main idea of our story, electric current. And to really, truly get it, I just want you to imagine a big flowing river. That's it. That one simple idea is the key to this whole chapter.
You know, in the last chapter, we spent all our time talking about charges that were just sitting there. Electrostatics, remember? To be honest, it's a little bit boring, no? It's like having a super fast sports car that's just parked in the garage. What's the point? We want to see it go.
Exactly. The real magic, the real fun, starts when we make these charges move. That flow is what powers everything you love, your phone, your video games, your Instagram scrolling. This organized, steady movement of charges is what we call electric current.
So here it is, the line you need for your exam. Electric current, which we call I for short, is the steady flow of electric charge through a conductor. And just like we measure how much water is flowing in a river, we measure electric current in a unit called the ampere. We just write it as a capital A. That's it.
Just look at this picture. See the water flowing through that pipe? Well, the flow of zillions of tiny electrons through a copper wire is just like that, a river of charge. If you can just keep this one image in your head, I promise you, the rest of this chapter is going to be super easy.
All right, we have our river. Now it's time to learn the one rule that controls this river. This, my bachas, is the superstar of the chapter, the one formula you must know. I call it the golden rule. It is, of course, Ohm's law.
Think about it. For a river to flow, it needs some kind of push, right? Like a downward slope. In electricity, that push, that pressure that makes the charges move, we call that voltage. The bigger the voltage, the bigger the push, and the stronger the flow of current. But what happens if our river has lots of big rocks in it, or if it becomes very, very narrow? That's going to slow the water down, isn't it? Well, in our electric wire, this kind of obstacle is called resistance. It's anything that makes it harder for the current to flow easily.
And this is where it all comes together. The beautiful, simple connection between our three friends, voltage, current, and resistance. V equals I into R. The push is equal to the flow times the obstacle. This is it. This is Ohm's law. Please write it down, learn it by heart, maybe even make it your phone wallpaper. It is that important.
So, can we change this resistance? Of course. Let's go back to our pipe. Imagine trying to push water through a really, really long and skinny pipe. It's difficult, right? Lots of resistance. So a longer wire means higher resistance. Now, what if the pipe is short and super thick? The water will flow so easily. So a thicker wire means lower resistance. See, it's just common sense. Okay, we've seen the big picture, the river. Now let's put on our superhero goggles and shrink down, zoom right inside the wire. Let's find out what those little electrons are actually doing. What is their secret life?
You know, it's actually total chaos in there. The electrons aren't flowing in a nice straight line. No way. They are bouncing around like crazy, bumping into things, going left, right, up, down. It's like a bunch of little kids running around in a busy market. But when we apply a voltage, we give them all a very, very gentle push in one direction. That slow overall forward motion, that is what we call drift.
And how slow is this drift? What do you think? Fast, like a race car, or slow? Well, the answer is going to blow your mind. Are you ready? It's about 1 millimeter per second. Yes, you heard that right. That is slower than a snail. I'm not making this up. This is from a calculation right in your textbook. Isn't that just unbelievable?
So, wait a minute. This raises a big question. If the electrons are moving slower than a snail, Why does your light bulb turn on the instant you flip the switch? How is that possible? Well, it's because the push itself, the electric field, travels at almost the speed of light, about 3 crore meters per second. It's like a long line of dominoes. The signal to start moving travels super fast, even if each electron itself is just taking a slow, lazy step forward.
Okay, we keep talking about this push, this voltage, but where does it actually come from? It's not magic, it comes from a source. And the most common source we see every day is, of course, a cell, or what you call a battery.
So what does a cell do? A cell is basically a little chemical pump. In our river analogy, to keep the water flowing in a circle, you'd need a pump to lift it back up to the top, right? A cell does exactly that for charges. It uses chemistry to give energy to the charges and keep that push going so the current can flow continuously. Now, every cell has a few important characteristics you need to know. First is its EMF. Think of this as the maximum ideal push the cell can give. It's the power written on the box. But just like a real pump has some friction inside it, the cell also has its own little obstacle inside. We call this internal resistance. So because of this, the actual push it gives to the outside circuit, which we call the terminal voltage, is a little less than its maximum EMF.
Okay, my champions, get ready. It's time for the final level. Sometimes in your exam, you'll see a circuit that looks like a big, complicated plate of noodles. So messy. For these situations, Ohm's law by itself is not enough. We need to bring out the big guns, our super tools, called Kirchhoff's rules.
The first rule is so easy, it's basically just common sense. It's called the junction rule. Imagine a point where a few water pipes join together. Whatever amount of water flows in, the exact same amount has to flow out, right? The water can't just disappear. Well, it's the same with current. The total current entering any junction must equal the total current leaving it. See? Simple.
The second rule is the loop rule. Picture this. You are going for a hike on a hilly path. You go up some hills, you come down some hills. But if you walk in a full circle and end up exactly where you started, what is your total change in height? It's 0, right? You're back where you began. It's the same in a circuit. If you go around any closed loop, the sum of all the voltage changes, both up and down, must add up to 0.
Enough of all this theory. Theory is good, but marks come from solving problems. So let's get our hands dirty. We're going to take a typical exam-style question, and we are going to solve it together, right now.
Okay, take a deep breath and look at this circuit. I know, it looks complicated. Lots of resistors, lots of loops. But listen to me, do not panic. We have our super tools. We have Kirchhoff's rules. We can absolutely do this. Our mission is to find the current flowing in every single part of this circuit.
Here is our step-by-step plan. It's so simple. Step 1, apply the junction rule. Just pick a junction and write down the current in equals current out equation. Done. Step 2, apply the loop rule. Pick a closed loop, any closed loop you like, and write down the sum of voltages is 0 equation. You'll need to do this for 2 different loops to get enough equations. Step 3, now you just have a couple of simple math equations. Just solve them using basic algebra. And that's it, you've done it. You are officially a circuit-solving genius, and you are ready for your exam.
So, my dear students, you are now masters of the flow. You understand how current works, but I want to leave you with one final thought. Think about it. What other things in life work like a circuit? Maybe the way traffic flows in a city? Or how our blood circulates in our body? Physics is truly everywhere. All the very, very best for your exams. I know you are going to do wonderfully.